Okay. So, George is sick, I think. And Andek, I think, is sick as well.
Maybe.
Maybe. Interesting answer, Matt.
Because Andek will never be absent.
Yeah, so.
He said he's sick. He wants it.
What did you think I said? Okay. Alright, let's continue. Where did we finish last time? Were we doing a section B or something?
Yeah, we're doing section B.
Section B, yeah. Could you open?
B2 or something?
Yeah, we'll continue with that. Do you happen to have any spare papers?
Yeah.
What, I might get a full pack. Oh, you're so kind. You're so kind. I'm so hungry. Thank you. I'll give you another pack later in the week. I'll repay you.
No, that's fine.
No. Because this morning, I went into the office, I went to take a packet from my box. Box was empty. So, it was because on Friday, I took the last pack, and I was thinking, I should throw out the box. No, I'll do that later. So then on Monday, I'm like, oh no. That's life. Okay. Can you open up Moodle? We'll continue. I kind of feel like the last question we did was a projectile question. Would that be right? No? Oh! Yeah, the spring one. I remember that now. Is that, what one was that? B1?
B1.
Yeah, so we are on B2.
Which paper?
End of semester 1, test 2016 to 17. 16 to 17.
Version 1? Maybe. We'll see.
Is there difference for version 1 and version 2?
Just different schools. I mean, the exams are different because they're for different schools. They give us the harder version because the DFC students are so much smarter.
Version 1?
Yeah.
Version 1 is easier or harder?
They give DIFC the harder version because the students are smarter here. I like that you believe me. Okay. There's no difference in the versions. It's just random. The reason they do this is because imagine you had a friend in Manchester. So they can't give the same exam to Manchester and Dublin. I mean, they're usually on the same day, but sometimes they're not. So maybe your friend in Manchester does the exam at 9 o'clock and you do the exam at 2 o'clock. It shouldn't be the same exam. Okay, did you open it up? Is question 1 the spring question?
Yeah.
Yeah, so we are on to 2. What's 2 about?
Turbo dynamics.
Siba, can you start reading B2, please?
A car engine is kept from overheating by water, which observes excess thermal energy. The water must then flow through a radiator to cool down. Water enters the cooling radiator at 100 degrees Celsius and leaves at 14 degrees Celsius. The specific heat capacity of water is 4,180 joules per kilogram per Kelvin. 2 kilograms of water every second flow through the radiator.
Okay, dokie. So I'm picturing 2 kilograms of water at 100, cools down to 40, and is the first question going to be something like how much energy or?
How much energy is lost every second?
Every second, yeah. Okay, so what formula do we need here? Is this A part 1?
Yeah.
What formula do we need here to work out the energy? Yeah, what is it?
Cm delta
MC delta theta, yeah. So what's the M?
2.
2. The C, 4180. And the delta theta? 60. And it's a loss. Okay. 120 times 4180 when you're ready. 50.
600.
So actually, that's 502,000 joules, or 502 kilojoules. How many marks for that, Siba?
3.
3? 3 is okay. It's only one formula, right?
Oh, and give the simplest unit for energy loss per second. Simplest unit.
Oh, so they want per second. So they want delta Q over delta T. So if we want to be the simplest unit, so then they don't want the kilo. Minus 500,000 joules per second. That's the answer. This is the simplest I can make the unit. Well, actually, no. I could make it simpler. Does anyone know what joules per second is? I think you know this one. Joules per second.
What?
Yes. Watts. That's the simplest I can make the unit. And the reason I put in the minus is to show the reader that it's losing this energy per second. Okay. Is there a part 2?
Yeah. Once the engine is switched off, the cap of the radiator is removed and 200 grams of water is allowed to evaporate. Taking the required energy from the remaining water, if 8 kilograms of water remain in the radiator system and the latent heat of vaporization of water is 334 kilojoules, by how many degrees will the remaining water cool down due to the evaporation? You may assume no other heat losses.
Okay, so what I'm picturing here is that there's 8 kilograms of water, but then 200 grams on the top turn into steam. So is the water on the top gaining or losing energy? It's gaining. And the water that remains in the tank here, losing. So we've seen this before. What equation do I make here? I say the energy that's gained is equal to the energy that's lost by the water. Yeah? So, what formula is for the energy gained? Now actually, what temperature is this water at? Is it 100? Yeah. Because they said they turned the engine off, didn't they? Yeah, it's 100, okay. It's not 100% clear that it's 100, like, maybe it's 60 or 40. What do you think? Where did they say the water was?
Hmm?
Did they say the 8 kilograms in a tank, or what's?
If 8 kilograms of water remain in the radiator system.
Ugh, that doesn't help. Because you know the radiator system at the start they said it cools the water down from 100 to 40. I really hate when the problem is English and not physics. We're going to go with 100 and see what happens. So what formula is it here for gain? What's happening to this 200 grams? What's the formula for gain? It's ml. And what's the formula for the loss? Well, that's just the water cools down a bit. MC delta theta. Now those are different m's, by the way. Actually, I forgot, what do they want? Is it the delta theta or something? It's the delta theta. Okay, so, well, alright, well that's just 0.2 times, what did we say, 334,000 you said earlier, wasn't it, Siba?
3349.
And that's 7.84180 delta theta. Well, actually, a good hint for how much work should be is how many marks. Is this a 3 mark? Don't say it's 4 marks, because that makes me, I know, you see, because that makes me feel like I'm doing something wrong, because there should be an extra thing involved, you know what I mean? Right, well anyways, we'll calculate and then check the answers. So if someone can type this in, please. Chow, maybe you could type this in, please? Yeah.
So I think it's 8 kilogram for loss.
Is it? Is it? Or is it 7.8? Could you read it again?
If 8 kilogram of water remain in the radiator system,
Yeah.
and the latent heat vaporization of water is 3.
Now, you know what, go back to the start of this question. Read the story again. Go for it.
Once the engine is switched off,
Mhm.
the cap of the radiator is removed and 200 grams of water is allowed to evaporate.
Okay, pause. So, I want everyone listening carefully. We just said the cap is removed and 200 grams comes out. We're trying to figure out, is that 200 grams counted in the 8 or not? Okay, continue slowly.
Taking the required energy from the remaining water. If 8 kg of water remain in the radiator system,
What are we thinking? I agree now with you, Matt. I think perhaps instead of 7.8, that should be 8. I'll be so angry if the marking scheme says 7.8. Right, Chow, sorry, I just need you to type this in, please. And Siba, maybe you could open up the answers while he's calculating that.
I did this question yesterday.
Mm-hmm.
I was looking at Mark's book.
And this is right? Okay.
Almost a 2.
Almost 2. 1 point.
997.
Ah. Yeah, so that's 2 Celsius. Nice. That's actually pretty good for 4 marks. When you're ready, Siba, is there a part 3?
No, there's B.
There's a B now, okay. Go for it.
Water can be used to cool hot metal walls when working to contain a fire in a building. The mass of a metal wall is 250 kilograms, and it must be cooled from 300 degrees Celsius to 150 degrees Celsius. The specific heat capacity of the wall is 450 joules per kilogram per Kelvin. Using data already given in the earlier parts of this question, calculate the amount of water at an initial temperature of 30 degrees Celsius, which could be completely turned into steam at 100 degrees Celsius. State any assumptions you need to make.
Okay. So, what's happening here, basically, you're throwing water at the metal wall to cool it down. And the wall cools from 300 to 150. So the wall, gaining or losing energy? This metal wall, what's happening to it? Gaining or losing energy?
Lose.
Lose. And the water that you throw on it? Gain. Yeah. So, let's first calculate the loss here. That's good old M C delta theta. Now we need to be careful with the water here. The water's gaining energy, but it's actually getting two types of energy. First, the water goes from 30 to 100, and then what happens? It evaporates. Yeah? So we actually have two formulas here. We have MC delta theta, yes, plus ML. (334) wasn't it earlier? So you can actually solve this. It's a simple enough maths problem. It's 250 times 450 times 150 over 4180 times 70 plus 334000. And that is the answer. How many marks was that, Siva?
6.
6?
There's assumptions you have to.
Okay, blah blah assumptions, right, I'll do that too. Assume no heat loss to the surroundings. Does that get my assumption mark? Okay, there's no heat loss to the surroundings, and the... What's the answer here, by the way?
26.9 kilograms.
26 point. Now guys, the question said, what are your assumptions? So the first thing is you have to assume no heat loss to the surroundings. So it's not like the metal is cooling down because it's on a cold floor. The second assumption, which was important, was that the steam stays at 100 Celsius. We didn't consider that the steam warms up, because really what will happen is when the water hits the metal and turns into steam, the steam rises away from the wall, so it doesn't continue the heat. Now, you know, if that door was on fire and I threw water on it, the steam would be at 100. But unless the steam could leave the room, the steam would continue to heat up. So, what assumptions did they have in the marking scheme?
Steam doesn't heat any further than 100 degrees.
That's it?
No heat loss from wall other than to water.
Wonderful. I get my assumptions.
No energy added
Ah.
to the wall by fire.
I don't get all my assumptions. The third assumption I didn't consider was that the fire is not continuing to heat up the wall. But, okay, fine. Right. Oh, I know what I can do. I can be sneaky here. I can say assume no heat lost or gain. So it's not gaining or losing any heat from the surroundings. Now that's a sneaky way to get those 2 marks in one go. Sneaky, right? No loss or gain to the surroundings. Yeah, wonderful. Okay, what's next? Part C or something?
Yeah. Once evaporated, steam can be treated as an ideal gas. The molecular mass of water is 18 grams per mole. How many moles of water are then in 1 kilogram?
Okay, so that's, what's that, like 1 mark?
Yeah, 2.
2 marks for taking 1,000 and dividing by 18? Okay. What's that? 500 over 9. 50, 50.4? 50.5? What's this, please?
55.6.
55.6 moles. Okay, what's next, Siva?
2. If this water is in the form of a gas at 300 degrees Celsius, What volume will it occupy at a pressure of 100 kilopascal?
So the pressure is 100,000 pascals, and the temperature, you said, is 300 Celsius. So 300 plus 273 Kelvin. That's 573 Kelvin is the temperature. And what were they looking for? I forgot already.
The volume.
The volume. So PV equals nRT. So V equals nRT over P. Right, let's calculate that. That's 55.6, 8.31, 573 over 100,000. And then we'll get the answer there. How many marks is that now?
3.
2.65.
2.65.
The
Yeah.
Kelvin, you have to. Can I add 273?
0.15, yeah. I was just being a lazy pig. Sorry. 273.15.
If I add 0.15, you'll be wrong.
No. I actually don't know what did they do in the marking scheme. Did they include the 0.15 or did it 273? Yeah, because I think that's what they do in chemistry, isn't it? Yeah, so I think they're the same like that.
Sir, temperature, why it's 5 centigrade? Isn't it 7 centigrade?
300 plus 273?
Yeah, but. They say it's 500 Celsius.
See, they told me 300.
No, that's part 3.
That's not 3.
Oh, right, yeah, okay. That's the next part. Yeah, we went to part 2.
Sorry.
You need more cocoa biscuits. Okay, go on. When you're ready now, we can do part 3.
If this gas was compressed to a pressure of 300 kilopascal and heated to 500 degrees Celsius, what would the new volume be?
Okay, so the pressure is now 300,000 pascals, and what's the temperature?
500.
So that's 773 Kelvin, because it's an extra 200. And what do you want now? The new volume?
Yeah.
So, it's exactly the same thing. Stupid question. Because all I have to do is go back on my calculator, change 573 to 773, and the 100,000 to 300. So backspace, replace, and the new answer is
1.19.
1.19 meters cubed. Now, how many marks was that?
2.
2. Okay, that's like 2 marks for free, because they just ask you to do the same thing but change the numbers. Is there more?
No.
That's the end of B2?
Yeah.
Right. I thought that was it was easier than B1. Agreed? Yeah. Okay. Shall we go on to B3? Electricity, right? Yeah, okay. Matt, give me B3, please.
A potential divider circuit can be used to provide an input for control electronics. For example, as a light sensor. A light-dependent resistor, LDR, has a resistance which decreases as the light level increases. Part 1. Draw a circuit diagram for a circuit with a battery as its power source, containing a resistor and an LDR and a potential divider, with the voltmeter placed such that the voltage increases as light level increases.
Oh, for flip's sake. How many marks is that?
4.
Is this A part 1?
A.
Right. Start again from draw. And then every time you say something, pause so I can draw it. Okay, so it begins with...
Draw a circuit
Yep.
diagram for a circuit with the battery as its power source.
Okay. Right.
Containing a resistor
Okay.
and an LDR
And an LDR
in a potential divider.
in a potential... Yeah, what indeed? An LDR. So, okay. I think I think what they're trying to do, very badly though, is, do you remember with our potential divider you have two resistors? Yeah? And one of the resistors you can usually change it. Do you remember that? I can't remember which one it is. It's usually the first one, the R1. Isn't that the way we drew it?
R1, yes.
Yeah. So I think what they mean is you have your battery, you have your switch, then you have your first resistor, which is the light resistor. That's the one where the resistance can change. I don't quite think that's the right symbol, so I'll just write underneath it. What did they call it? LDR, wasn't it? Light dependent resistor. And then there's a second resistor. And then where did we put the voltmeter, did it say, if you continue?
With the voltmeter placed such that the voltage increases as light level increases.
That's what I'm thinking. Did it say the LDR decreases its resistance when the light increases?
Yeah.
Yeah, okay. So you're right, Siba, we'll stick the voltmeter. I see. So it said put the voltmeter so that it decreases when the light increases. Is that what they said?
With the voltmeter placed at such that the voltage increases as light level increases.
Ah. So what happens if you look here, when the light shines on this, the resistance here drops, which means the voltage drops here. So that means this voltage must increase because the total has to be whatever the battery is. So, and anyways, we usually put the voltmeter on the second one to begin with, don't we? In the pictures I've been drawing for you. This is a very difficult English here, very difficult English. But I think this is how the picture should look. It's a hard work for 4 marks. Is that the end of part 1?
Yes, sir, but do we have to draw the correct LDR symbol?
I don't actually. The problem, Matt, is that this is the first year that they had this on the exam. So it hasn't been in any previous exam, nor is it in the syllabus. So I actually complained saying that students aren't familiar with this symbol. Now, you have the symbol for the LED diode, but that's not quite the same thing as an LDR.
The mark scheme says 1 mark goes to LDR symbol, correct?
And does it show you what the symbol is?
No.
You going to Google LDR symbol, please? Fudge. So it's a resistor but with a circle around it. Okay.
And
And
arrows.
And an arrow?
2.
Where? Oh, for the light. Well, there's my 2 arrows there. I nearly had it. I just need to put a circle around it. See, this is my problem. Remember the table I gave you with all the diagrams in it? I used what they've asked in the exam for the last 12 years to make that table. So this guy was a jerk because he put this in when it hasn't been in any previous exam. So now I'm like, well, what do I do? Because I feel like the only way to be safe is if I show you every symbol. But there are many symbols which you don't need. You know, like DC motor, AC supply. You don't need these in semester 1. So I think that was a bit of a jerk move. Okay, what is part 2 here?
If the resistance of your resistor is increased, but everything else remains the same state, and explain what will happen to the voltage measured by the voltmeter.
Is this what they're calling your resistor? Or do they mean the other one?
If the resistance of your resistor is increased, I think it's a
But but you have two resistors.
I think the second one.
That's what I would have thought. You think the first one?
Yeah, because it's increased. The second one increase is stay constant.
If you put in a new resistor. But you're right. Okay, well, but this is annoying me because why didn't he just say LDR? Why did he have to say your resistor? I don't know. So anyways, what was he saying? The question is, if the resistance increases, what happens to the voltage?
Yes.
Okay, well, if the resistance increases, then the voltage increases. How many marks? 1 mark?
3.
No, that can't be right. Is it 3 marks? And is it right?
The mark 2 says voltage increases.
3 marks.
And voltage increases, either total resistance increases. Current through.
Oh, hang on, pause. Did the question say what happens and explain why?
Yeah.
Oh, sorry, I didn't do the why part. Is the question said explain why?
State and explain what.
And explain, okay. So that's why it's 3 marks, 'cause I have to explain. Okay, so why does the voltage increase? Well, let's have a look here. Could simply say because R increases and you have the triangle VIR, so V equals IR, which means V is proportional to R for constant current. So basically, if you increase the resistance, the formulas tell you that the voltage has to increase. Okay, what's the next part now?
B.
B? Okay.
To protect ammeters from damage, they are often found with a diode or LED connected in parallel with them in circuits. Explain how this precaution might protect an ammeter.
So they want to know what's so great about having this in parallel with the ammeter. Do you remember what happens with the diode? You have the. Do you remember the graph for it? It goes like this. Yeah? Isn't that what it does? So, can I scroll down to explain why this is a good thing to help protect this? The ammeters can easily break if the current and the voltage become too large. Now, this is the problem. If you have this in parallel with your ammeter, you're actually changing the circuit. And you might say, well, it'll affect the readings of the ammeter. But look, let's call this R1 and this R2. What's the total R? That's 1 over R equals 1 over R1 plus 1 over R2. Now, if I just write this as 1 over R equals, this is R1, R2 over R1 plus R2. So I get R equals, what's that? R1, R2 over R1 plus R2. Now, if the R1 is small, and it will be small if the current is small, because remember for the diode, oh sorry, I said that the wrong way. If everything is small, then what's the resistance here? It'll be big. The R1 will be big. So you can think about it like this. If the R1 is big, then which one here will be bigger? 1 over R1 or 1 over R2? This one here will be. Because if the R1 is big, this is 1 over a big number which is small. So you actually can forget about that. So then you get 1 over R equals 1 over R2. In other words, you can actually forget about the R1 when it's big in parallel. But if the current becomes too big, then what happens to the R1? This will become small. So if the R1 is very small, then which is bigger, the left or the right here? I'll actually need make some more space here. Which one's bigger? 1 over R1 or 1 over R2? If R1 is very small. Which? 1 over R1 is bigger, isn't it? So you have 1 over R equals 1 over R1, and you don't care about this because this part is so big, because the R1 is so small. So then you get R equals R1 then. And in the other case you have R equals R2. In other words, when the voltage is small, most of the current goes through here, and it's like you have no R1. But when the current is big, most of it goes up here, and not much goes down here. So in this way, it protects the ammeter from large current, but doesn't affect the reading when the current is small. This should remind you of something you might have learned in middle school, where it says current takes the path of least resistance. Did you ever hear that before? You've heard it before? You've not? You've heard it? So it's the idea that if you have two paths, this one has a big resistance and this one has a small resistance, most of the current will go through the path with the lesser resistance. Most will go here and some will go here. That's the kind of idea. So when the current is small, this is big, so most of the current will go down the bottom. And then vice versa. So let's put this in a sentence. When I is small, the current goes through the ammeter as the LED has high resistance.
How do you know LED types?
Oh, we did the graph. Do you remember? The LED diode one, yeah. We even marked off the number where it changes. What was it, like 0.7 volts? Yeah. When I is small, the current goes through the ammeter as the LED has high resistance. However, when I becomes large, the current diverts through the LED as the resistance drops. Oh, goodness sake, how many marks is that?
3.
Oh, worked so hard for 3 marks.
When I becomes...
Sorry, my handwriting's terrible. I'll read the whole thing. When I is small, the current goes through the ammeter, as the LED has a high resistance. However, when I becomes large, the current diverts through the LED as the ore drops. Oh, hang in there, Siva. Did you have your cocoa biscuits? And you're still low on energy? Might need to go to the mosque today. I had their spicy spinach lamb dish last Friday. You know the one, the green one, the lamb in it? It's actually, he says it's spicy. You know this one? Have you tried it? Did you take the vegetarian one?
I ate that. Oh, thanks for having me.
What do you usually get there?
Chicken masala.
Yeah.
Or
That
it's
one.
a
Huh?
Or it's a carrot.
Oh, you get the wraps there. Haven't tried the wraps yet. Are they big? Expensive?
Like 6.
Okay. But it'll fill you up?
Oh yeah.
Okay, good. Good. Alright. Is there more to this?
Yes. Part C.
Okay.
In the real world, batteries and other power sources contain unavoidable internal resistance. We wish to investigate this using a simple circuit. Part 1.
I'm way ahead of you. It's going to be draw the circuit, isn't it?
Draw a circuit to include a battery and a method for varying the current, which will allow you to investigate the terminal voltage of the battery at
sorry. I drew my variable resistor on the side for some reason. I don't know why I did that. Okay. So I have to stick on my voltmeter. I have no idea why I put that there when I usually put it at the bottom, but what difference does it make? Do you know what? I'll put the switch at the bottom. We'll be safe. We'll put a switch on it. We can close the switch. So, the marking scheme, it's going to give you a mark for the voltmeter, the variable resistor, the ammeter, the cells, and the internal resistance. Probably no mark for the switch. How many marks are drawn on this diagram now? 3. It's not fair. They gave us 4 in the beginning when we drew the other one. I don't like this question. Don't.
Yeah.
Yeah, you too. Yeah.
Many explanations.
Too many.
Sketch a graph. Part 2. Sketch a graph of what you would expect to see and explain how you use it to find the EMF of the battery and also the internal resistance of the battery. 5 marks.
So, you plot the voltage against the current, and you usually get a graph that goes down like this, right? And this graph is nice because on the graph it contains 2 pieces of information. So where it crosses the y-axis here, that is the EMF, the voltage of the battery. And then the internal resistance is equal to minus the slope of the graph. And that's how you would get both. So how many marks was that? 5! Oh wait, now we have to be careful. Are they looking for you to explain what you do in the experiment?
Explain how you would use it to find the EMF of the battery.
Now this is a good question. Is the equipment or the graph?
Graph.
Yeah, graph.
But are you sure it's the graph and not the equipment?
I read the
Maybe you have to read the previous sentence.
sketch a graph of what you would expect to see and explain
Ah.
how you would use it to find
Okay.
the EMF of the battery.
Okay, so the it is referring to the graph and not the equipment.
And also the internal resistance of the battery.
Yeah, but that's it there, isn't it? This can't be right. 5 marks for this. Maybe I'll have to write the sentence. The EMF is equal to the y-intercept on the V against I graph. And then what's the internal resistance equal to? Is equal to the minus slope of the V against I graph. But to be honest, if you kind of wrote this in the exam, to me it's clear that you're telling me this is the intercept, which is the EMF, and that the resistance is the negative slope. But because it's 5 marks, it feels weird not to do a little bit more work. So I wonder, what did the marking scheme do?
Oh, V on y-axis.
Yep.
Current on x-axis.
So that's 1 mark for this.
1 mark for both.
Oh, for both? Okay.
Then straight line,
Really? Okay.
negative gradient.
Okay, so the straight line is going down, fine, yeah.
Statement of EMF equal terminal volts plus lost volts in any sensible form or equation.
The y-intercept.
Statement of EMF equals terminal volts plus lost volts.
Terminal volts is what
Oh.
I just.
Terminal volt plus lost volts, yeah?
There's another one.
Oh, good.
Relate to Y equals to MX plus C,
That's the one.
where Y equals to terminal voltage. Then, so gradient equals to negative R.
So the gradient is equal to,
Negative R.
yeah. Okay. They're not being really clear about the EMF, but they did say you can relate it to the y equals mx plus c. But did they actually say in it that it's the c?
Oh, and C equals intercept equals EMF of battery.
Good, okay, alright, right. 1, 2, 3, 4, 5. Good, okay, we got our 5 marks. That actually was a nice one to finish that rather messy question on. There isn't any more, right?
Yes, there are. There's one last one.
One last one. Okay, what's the last one? Part 3?
Cars have batteries of around 15 volts EMF. Starting a car requires a large power supply to an electric motor. Explain why, when starting a car, other items in the car such as the headlights and radio go dim or switch off.
They've asked that question 10 years ago. I remember it. 10 years ago. So he obviously looked at this question and thought, yeah, I'll ask it again. So they want to know, so the question is, in your car, I don't know if you've noticed this, when you turn the engine on at the beginning, if you had the lights on, the headlights, they dim slightly as you turn the engine on. Now I don't really know if new cars do that, or if it's an older car thing. You know, like if you turn the ignition on, the lights dim for a moment. I don't even notice that.
The radio bill.
Yeah, but I don't know, like, would it do that on the new cars? Anyways, what he's getting at is that when the key is turned, so for the car to start, you need a very high voltage at the beginning to get the, what's it called, the ignition going. You know that part of the car that creates the spark to make everything start, the ignition motor. Is that what it's called? So when the key is turned on, the ignition, I don't know how to spell that, the ignition requires a high, the ignition puts a huge demand on the battery, thus leaving less power for everything else. So that ignition, the starter, that's what it's called. The starter. You know the sound of it when you turn the engine on. It's the part that goes, when it's broken, it goes, you know, when the car doesn't start, you hear that sound. That's the ignition not getting enough power to start, maybe because your battery's dead. Yeah? Sorry, I'll read it. When the key is turned on, the ignition puts a huge demand on the battery, thus leaving less power for everything else. Yeah? What did they say in the marking scheme?
Large power requires large current. And
It's like Spider-Man, you know, with great power comes great responsibility.
when large current flows, potential PD is lost across internal resistance of battery. So terminal voltage drops, causing items to switch off.
That's a very advanced answer. I mean, it's not like we're doing a mechanics engineering course. I wonder if I would have gotten full marks for my answer. How many marks was it? 2. Yeah, I think maybe I'll give myself 2 marks. Close enough. Yeah. The problem with definitions and explanations is this. Sometimes the question is quite clear. So they might say, explain something by referencing something else. So, an example in English might be, explain the problem of obesity. Now, if you just stop there, you realise, there's many explanations you can give, and maybe there's only one answer that they want. So, to make it a bit clearer, they'd say, explain obesity and give reference to sugar. So then okay, well, people are eating more sugar. So the problem with this question is, it didn't give us any hint on what we are supposed to be talking about. I think it just said, explain why the lights go dim. But there could be many reasons. Maybe you just have a bad car. Right. Is that the end of B3? Okay. So, was that version 1? Yeah, so we still have one more exam to practice. I think there's a version 2 there. Now, what are you thinking? Do you want to try section A first, or do you just want me to start doing it? What are the feelings? Yeah, have you done it, section A? No. So this is a new set of questions. How many marks is section A? 60, is it? 60? Okay. Do you think it would be possible to finish section A before lunchtime? How many questions are there in this section A?
11.
11? No, that's a bit too much, isn't it? If you got the first 6 or 7 questions done, that'd be great. You can do the first 6 or 7. Yeah?
Can we do questions without not mechanics?
You don't like mechanics anymore?
Maybe we are a bit familiar with mechanics, but not other topics.
So, maybe you guys want to... You want to skip the mechanic questions right now in section A. No, you see, no, look at the...
Okay.
Well, anyways, I tell you what, try your best to answer all of them, and then in the next class we'll do all of section A. Chow, could you put the light on, I think?
This room is so cold.
It's a little cold. How do the questions look? First one is a mechanics. Yeah, that's okay. You have to resolve, cost and sign. Yeah. Try your best, Chow.